any element of this can be written in this form, or it was ls, I'm sorry, not SL, but ls, L square S, etc., with possible S epsilon, S to the power epsilon here, where epsilon is 0 or 1. And an element of this boundary is what? An infinite sequence of this kind. So again, S to the power epsilon, another epsilon prime. So ls to the power n0, L square S to the power n1, but this times infinite. This is a finite product of this kind, ls to the power, let's say, nk. And the action of this is just precomposition. I just add this to the front of this, and this gives me an action. Alternatively, this gives us a continued fraction, which is n0 plus 1 over n1 plus etc. And here, this element can be written as a linear fractional transformation, ax plus b plus cx plus d. And if this is x, the action is simply given by this operator sending this number to ax plus b over cx plus d. So this is a very nice description of this action. Sometime during my talk, I'm going to talk about the action of PSL2Z on the upper half plane, which I denote by H. This is the set of complex numbers with positive imaginary part. However, in a very strange way, this action admits no simple description. So this thing acts on complex numbers, but complex numbers has no such standard continuous fraction expansion, so that we can describe the action in this simple terms. Anyway, this is a very interesting and important action from which we can deduce some facts about the group PSL2Z. But before going into that, I'm going to talk about the last action we have seen. So the modular group acts on F itself, not on its boundary, but on itself. So this action was defined through this action, which implies that any of subgroup, if gamma is any subgroup, then that subgroup also acts on F. From this action, we are going to describe the action of this group on sub PSL2Z, which is the category of subgroups of PSL2Z, and the arrows in the category are simply inclusions. So I say category, but you can see this as simply as an ordered set, partially ordered set. So inclusion endows this set with a structure, and gamma acts on this set by conjugation. It sends any subgroup to another subgroup by conjugation. So one of my aims in this talk is to describe this action in quite concrete terms. So what was the action of PSL2Z on F? Edges of F were simply indexed by the set PSL2Z, and here I have PSL2Z, and if I have an element M here, then it sends an edge named W simply to the edge named M times W. This is my action. So it is easy to check that if I do this in this manner, this action preserves the vertices. It sends vertices of degree 2 to vertices of degree 2, vertices of degree 3 to vertices of degree 3, so as to preserve the incidence relation. So this is indeed a group action, which is something good. However, so this, by the way, F For a moment, we are going to view this not just as a simply abstract combinatorial graph, but as a topological object. So we identify its edges with the unit interval, 0, 1, so that it's going to be a topological space. So we have a group acting on a topological space. However, we saw yesterday that this action is not free. It has some fixed points. And what are those fixed points and elements which fix some points here? As we have seen, S, for example, or more generally, any finite order element fixes a point, and by point I mean vertex of F. So let gamma be a subgroup PSL2Z which acts freely. On F. And this is equivalent to say that it is easy to check also that if and only if gamma has no torsion elements. Torsion element means simply an element of finite order. So now we have a group acting freely on a space, on a topological space F, so that we can consider the quotient object, the quotient topological space. This quotient topological space is going to be a graph. So the topological space F quotient gamma, or, well, since this is a left action, I must write this as F quotient gamma, is a graph. Moreover, from the very definition, it is easy to check that this action preserves the ribbon structure. So it doesn't, as I explained yesterday, it preserves the ribbon structure of the tree. So it is a planar. This group is a group of automorphisms of the planar tree, not just abstract combinatorial tree, but of the planar tree. Since it preserves this ribbon structure, that is simply the orientation of each vertex as W, WL, WL square. So the vertex named W, WL, W square is cyclically, the edges emanating from this vertex are cyclically ordered in this way. And since this action of the modular group preserves the structure, any subgroup of the modular group does the same. And this endows the quotient graph with a ribbon structure. So this is a ribbon graph. So I have a finite graph, something like this. I may have a finite or infinite graph, but I have some graph like this. It may have some loops. It is not a tree anymore in general, something like this. However, around each vertex, and orientation, cyclic orientation of vertices emanating from that vertex, like this. So in general, such a graph cannot be drawn on the plane. It is not going to be a planar graph, but any such graph can be more or less canonically embedded on a topological surface, on an orientable topological surface, so that the orientations, that is cyclic ordering of edges given by the orientation of the oriented topological surface coincides with the ribbon structure of the graph. So it can be drawn. This graph is naturally or lives on some oriented topological surface. And how to construct that topological surface? It can be easily constructed this way. Since I have those orientations, I start from one edge, and I always I travel along the graph by always turning left or right, it doesn't matter. But if I always turn left, then I'm going to make a loop and come back to the original point eventually. So I'm going to have something like this here, and I fill this with a disk. And well, for some reason, this disk must puncture. So every time I have such a disk, I glue a punctured. Every time I have such a loop, I glue a punctured disk. So here we see another loop like this. I start from this edge, and I travel inside the graph by turning always left. Then I come back to the original point. So I glue another disk here. If I do this for every such loop, I end up with a topological surface, which is not the plane in general. I'm going to give you some examples. For example, one of the first subgroups that I gave you was this. Well, I gave you the exact sequence to sigma 3, which defines us a subgroup. And the quotient, if this is gamma, then the quotient surface is the topological P1C, or let's just write S2, minus 3 points. So if we only look at the graph looks like this. So I'm going to have 2 points of this type and 3 vertices of this type. And the gluing procedure is like this. So I have one loop here, so I'm going to glue a disk here, a punctured disk here. I have another loop here. I glue another punctured disk here. And if I travel along the exterior sides, I have another loop, and I glue one more disk there. And by gluing those 3 disks, I think it's convincing that it will give you a thrice punctured sphere, which is a quite important object in arithmetic algebraic geometry and some other fields as well. So this is the one simple example. Another simple example is the following. If I consider the kernel of the abelianization, that is, if I consider the commutator subgroup, then the corresponding graph this time will live on a torus with just one puncture, and the graph will look like this. So something like this plus something like this. So I have two vertices of degree 2, degree 3, and I have here, and here 3 vertices of degree 2. So what happens in general? In general, I'm going to have some Riemann surface like this after the gluing procedure with some holes, handles, and also with some punctures. Just typical. I mean, you may draw infinitely many such graphs on this, but just one example, just to give you one example, it could look like this, let me remove the punctures because it's not easy to identify them. So, well, another thing like this, another thing like this. So, not, well, you can of course draw infinitely many graphs, many graphs on a given topological surface. However, if this surface is constructed from the graph the way I described, then the complement of the graph inside the surface must be a set of disks, okay? And it is not very easy to do that. Given a topological surface, you draw a graph on it so that its complement is a union of punctured disks. So this is the general situation, and I would like to concentrate on this a little bit more. So on the other hand, conversely, given such a graph, what kind of graph? It need not to be drawn on a topological surface, but it is enough that it must be of this kind. Graph with a ribbon structure, which is bipartite. Bipartite means that its vertices are split into two parts, here red and white, so that no two vertices of one type, for example, type red are neighbors and white are never neighbors. So red is neighbor to white and white is neighbor to red, but red is never neighbor to red and white is never neighbor to white. So that kind of graph. So that plus the vertices of type red are always of degree 3, and the vertices of type white are always of degree 2. So if I have such a graph, then, well, let us call this graph G. Then G is isomorphic to F over gamma for some what? For some gamma subgroup of the modular group. This again comes from the topology, because we know that I know that if I have such a graph, for example, this graph, or let us give another graph, for example, this graph lives on the sphere, so I have two vertices of degree 3 and 3 of degree 2. If I have such a graph, then it is easy to see that its universal cover is the 3, is the failure tree. Why? Because to construct universal cover, I can cut this from here to here, here and here. Then I can, well, let us open this a little. Then I can obtain, I can take infinitely many copies of the same thing, and I can glue them. Each time I glue the same thing, what kind of thing it is? So each time I glue the same, I take infinite copies of this and I glue here and here and I go on like that, and I end up with a 3. And this is going to be the universal cover of this graph in the very topological sense, if I consider this as a topological space. So we see that the universal cover of this space is 3. Okay, since the universal cover of G is the failure tree. And which means that any such graph corresponds to a subgroup. But that subgroup must be torsion-free, because the usual Galois correspondence from topology applies to free actions only, right? Fundamental group and free actions. So what is that correspondence? If I have some space X, then, and if it's universal cover X tilde, then there's a one-to-one correspondence between subgroups of pi1X and coverings of this space. So this is exactly the same correspondence, which classifies us torsion-free subgroups of the modular group in a quite concrete manner, right? So this says that for any graph of this type, I have a subgroup of the modular group, which is torsion-free. However, this correspondence is not one-to-one. This correspondence is not one-to-one because in order to make it one-to-one, I have to single out an edge of this. Okay? If I pick an, moreover, if I decide, because what is the topology? From topology, I know that this correspondence really applies to base-pointed subgroup space with a base point and its subgroup. So it corresponds to coverings of this space with a base point. So any subgroup of this gives us a covering of this with a base point. So I must single out a base point, and if I do that, every such graph will give a subgroup of the modular group. So I'm going to describe how. For example, take the one we just discussed. This graph. And imagine that instead of taking just one single base point, I'm going to take a base edge, which is more practical. But this is almost the same thing from topology, because this thing is contractible, so it doesn't matter. I can pick at a base point. What is the subgroup which corresponds to this one? The subgroup corresponding to this one is, I can, if I write this as I can turn left once, so left, and then I pass to the other side by ls, and I again turn left. If you straight yourself here, then coming here amounts to taking one left. So this is SL. And if I do the same thing here, if I come here, it will be S, here be SL, here it will be SLS, SLS square S, and here SL square S, L square again. So the conclusion is that the corresponding subgroup, gamma in this case, is the subgroup generated by LSL and SL square S, L square. SL square, SL square. Well, I have one more S because from here I must come back to here, S. I hope that this is clear. So we can, in fact, say that this is, in fact, precisely the fundamental group of, if I call this G, this is the fundamental group of G based at I. Again, I repeat, this is the usual construction from topology, where you have some, if you have some intermediate cover with a base point, then pi 1 y star is nothing but x quotient. If this is a covering of this, then this is a quotient of this by pi 1 y star. And we are talking about the same correspondence. And I hope that given now, if I give you any graph like this, you'll be able to describe its fundamental group and write down the following corresponding subgroup of which quotient by f gives this graph. Okay, I think that the procedure is quite understandable. Well, let us write down this as an exercise. Well, non-planar graphs are somehow hard, but draw a graph which may be planar of this type and determine its fundamental group as a subgroup of PSL2Z. What about the conjugation action on torsion-free subgroups? Well, let us here instead consider another base point. For example, this one. If I pick this point, this base point, then if I apply the same procedure, I'm going to obtain what? I must turn right once, so this is my new I. Let me call this I prime. So I must turn right once, so L square, then S, L square S, and then again L square. And now I have to do this, so I have to start with an S, and then I'm going to have, well, S, L, S, L, S. Okay? So if I change the base point, I obtain this one. Now, it is easy to see that this is just a conjugation of this subgroup. Let us call this gamma prime. This subgroup is just the conjugation of this subgroup by S. I moved only by S here. I just came from here to here. So that the new subgroup is not the same subgroup anymore, but it's a conjugation of this subgroup. Well, because if I conjugate with this S, I'm going to put one S here and one S here. Because, well, I must write S to the power minus 1, but S to the power minus 1 is S. S is involutive, so I just put S. And if I do the same thing here, this will cancel out. So this will be SLS, LS, and so since these two will cancel out, I'm going to have these ones, so which gives me precisely this subgroup. So conjugation of this by S gives me this subgroup, which is true in general. So if you pick such a graph, for example, and pick this as a base edge, and if you pick, for example, this as a base edge, then the corresponding subgroups will be conjugate subgroups inside the modular group. So now I realized a part of the promise that I promised you. That is to say, I described the action on the subgroup, on the set of subgroups, but torsion-free subgroups, not all subgroups, of the group PSL2Z by conjugation. What does it do? It just changes the base edge. So I repeat, a subgroup of PSL2 is nothing but a graph of this type plus a edge, a base edge, and the conjugation action moves that base edge. That is to say, if we quotient this structure by the conjugation action of the modular group, we end up with the set of modular graphs, which I'm going to call these modular graphs without a base edge. So we can say that a modular graph, a graph of this type is nothing but a subgroup of the modular group up to conjugation. So the graph itself is a subgroup of the modular group up to conjugation, and if I choose a base edge, then this pair will determine me a subgroup. Not a conjugacy class of a subgroup, but just a subgroup. So let us now generalize this situation to torsion groups also. What can we do in general? So if we try to do this for torsion subgroups also, we encounter a trouble, little trouble. And the trouble is this. If I quotient F, well, what is the simplest torsion-free subgroup of PSL2Z? It is PSL2Z itself. Of course, the trivial subgroup perhaps can be considered as a torsion-free also, but, well, anyway, the second simplest is the modular group itself. And we see that the action of the modular group on the set of edges of F is nothing but the left regular action of the modular group on itself, because the edges of the modular group are parametrized by the modular group. The edges of the fairy tree F are parametrized by elements of the modular group itself. So there is just one orbit. I repeat. So EF is PSL2Z, so that this action is going to have just one orbit. And if I look at the quotient space will look like this. 1 point like this, 1 point like this, and this. Just a single stick. So from the purely topological point of view, this space is simply connected. So it has no coverings. So it should not be possible to apply this topological correspondence. So let us repeat here FIF, and here I have F over PSL2Z, which appears to be, which is seemingly simply connected, so that I cannot apply this correspondence. In order to do that, I have to extend my notion of a topological space, and there are several ways of doing this. For example, I can consider orbifolds. I can consider this as a one-dimensional orbifold and study its coverings. Another way of doing this, which is much more technical, is to use algebraic stacks. However, well, orbifold terminology is somewhat simpler. The algebraic stack terminology is much more sophisticated. But anyway, there's an alternative. I'm going to take an alternative approach of handling this problem, of dealing with non-free subgroups. So, in this case, in general, let gamma PSL2Z be any subgroup. Then the graph gamma, quotient, F quotient gamma is constructed as follows. And there's nothing subtle about this construction. You can figure that out by yourself. First of all, the set of edges of gamma quotient F is going to be the set of edges of F quotient gamma. That is to say, it is going to be just the set of gamma quotient PSL2Z. So in general, this is not a normal subgroup. So this is not, the quotient is not gamma. In that case, I consider only the set of cosets of gamma. So we equivalently, this is the set gamma times W, where W is in PSL to Z. And vertices of type of degree 2 in F over gamma is just the gamma orbits of vertices of degree 2 under gamma. Similarly, same for the vertices of degree 3. This is gamma times W, WL, W square, where W is in PSL to Z. And incidence, I have to define the incidence as well. This is a little bit more involved. I'm just going to write it down. So, two vertices V prime are incident if and only if V intersection gamma V prime, which is defined to be the union mu in V, mu prime in V prime, mu intersection mu prime is non-empty, and which is a gamma coset if non-empty. So these two are incidents if and only if this is non-empty. Well, incident if and only if non-empty. And if this is non-empty, this is a gamma coset, and the edge between V and V prime is exactly this gamma coset, because the edges are itself gamma coset. So you can verify this. Check that this defines us a well-defined incidence relation on the graph gamma, and it is the desired incidence relation. In particular, it gives the same thing from topology that we have just discussed for torsion-free subgroups. So with this definition, gamma over F is a graph, a bipartite ribbon graph with vertices of type 2, which are of degree 1 or 2, and with vertices of type, this type of bullet type of degree 1 or 3. And moreover, well, first of all, let us name these graphs. These will be called modular graphs. So all the graphs I have drawn on the table were modular graphs. But there are more modular graphs than this. Let me note that if you construct the modular graph this way, so in general, well, let me say that a graph which is isomorphic to a modular graph is also called a modular graph. So to be more precise, notice that by construction, this quotient graph comes with a special edge. The one which is the one labeled gamma. So edges of the quotient graph were cosets. So if I pick the coset which is gamma itself, then I'm going to obtain a special edge, and that special edge is going to be the base edge that we previously described. And then it will be so that we can define the notion of a fundamental group of such a thing. It is going to be a kind of orbifold. So one can define the fundamental group. It is quite automatic if you start working with this, how to define it. So one will have that pi 1 f over gamma base that special edge, which is gamma, is going to be isomorphic to gamma. So it is, again, I didn't do that, but it is possible to define the fundamental group of such a graph so that its fundamental group based at that special edge, gamma, is going to be the group gamma itself. So instead of explaining this theoretically, how to define the fundamental group and so on, let me give you some examples. It will be more direct and it will be more understandable. For example, we can start by constructing the graph f over PSL to z itself. So this is going to be a graph with two vertices like this, and with just one edge, as we noticed there. And, well, the edge, the name of the edge will be just PSL to z, because there is just one orbit, and that is the orbit of PSL to z in this case, because the action is the action of the PSL to z. And this edge is going to be PSL to z I W, I L square, and this edge will be PSL to z I S. So perhaps it is necessary to reinstate my claim in terms of this graph. I claim that it is possible to define the notion of a fundamental group of this, which is apparently simply connected. However, we can define the fundamental group of this, which is based at this edge, so that this fundamental group is precisely the modular group in this case. So this single stick has the modular group as its fundamental group. And because of that, I call this the modular stick or modular interval. We are going to see how this interval, modular interval, appears in the geometric setting as well. But before going to examples, let me write down everything that I claimed until now. Theorem. There is a one-to-one correspondence between modular graphs plus a base edge on the one hand, and subgroups of the modular group. So this includes torsion or torsion-free subgroups, everything. And we can you can prove this theorem by yourself. There is a one-to-one correspondence between modular graphs with two edges, two chosen edges. Can anybody guess what I'm going to say now? This is a correspondence between. So here I must say something which is related to gamma, which is related to the modular group. Can anybody guess what I'm going to write here? Nobody? Okay, so let me write it. Cosets of subgroups of PSL2Z. And one more thing. This is something that I have almost proven. Also, there is a one-to-one correspondence between conjugacy modular graphs and conjugacy classes of subgroups of PSL2Z. Okay. Well, for some purposes, I like to denote this set of modular graphs as the category of coverings of the modular interval with base edge. So this is also a category. These are the coverings of this space. And this side, I like to denote it as subgroup of PSL2Z. So the first claim says that the coverings of the modular interval and the subgroups of the modular group are in one-to-one correspondence. And here we denote this simply this, coverings of this without base edge. And here we can write perhaps sub star PSL2Z. This is the set of conjugacy classes of subgroups. No. I should have written this here. This is this here, and this is sub star PSL2Z here. Well, I have no name for set of cosets of subgroups of the modular group. I think that this result is important from several points of view, and it is mostly for educational purposes, perhaps. First of all, this is if you followed a course on algebraic topology, there you learn the theory, the homotopy theory, fundamental groups, covering correspondences, etc. However, this is the one single occasion where you can realize this correspondence in a very explicit manner. You can visualize almost everything in terms of graphs. So this is also somewhat interesting from the point of view of group theory, because in this case, you have a group which is quite big, and you can describe all of its subgroups in a quite explicit manner. So I think that this might be a good opportunity to, this is a good occasion to look inside some unknown group and know almost everything that one may know about it from the group theoretical point of view, at least as a start. Of course, once we do that, there are infinitely many more questions about its representations, etc., which is another matter. But I think that this gives a quite good understanding of the group theoretical structure of the modular group. So let us give some examples. So first of all, why I said covering of this modular interval, how to construct the covering of this, you take infinite number of copies or finite number of copies and you glue them. For example, if you glue 2 copies, you are going to have a degree 2 covering. And by the way, most of this story can be generalized to the group Z over NZ, free product Z over MZ. You can generalize almost everything I said to other free products. So how do I construct the covering of this space? So, which appears to be simply connected, but is not, because this fundamental group is PSL to Z. I can take 2 copies of this and glue them like this. So this is going to give me a degree 2 covering, which is also Galois necessarily, because there's a Z over 2Z action on it. And this action identifies these 2 parts, and the quotient space is going to be just modular interval. So this is going to be a covering. And now, what I can do, I can take 3 copies of this and construct this thing. Okay? Now this is going to be a covering of this by Z over 3Z, because there's an obvious Z over 3Z action here, and the quotient space is this one. And there is a Z over 2Z action in here. However, this is not a Galois. So this is a Galois covering of this one, this is a Galois covering of this one, and this is not a Galois covering of this one. Well, in the group theoretical terminology, the fundamental group of this is a normal subgroup of the fundamental group of this, and the fundamental group of this is a normal subgroup of the fundamental group of this. However, the fundamental group of this is not a normal subgroup of the fundamental group of that one. So this also illustrates some well-known group theoretical fact. Normal subgroup of a normal subgroup need not be a normal subgroup. It can be non-normal. And how much time do I have left? I have something like half an hour, right? No? I must finish now? I started a bit later, okay. Well, it's PT, so I need something like 5 minutes to finish, if it's okay for you. So, modular graphs looks like this. So, they may have pending edges. Whereas, if I quotient by free subgroups, I don't have such pending edges in the graphs. Pending edges of type this or type this. For example, here I have a pending edge of type this. So its degree can be 2 or 1. Here, if it's of this type, its degree can be 1 or 3. So now we can take a general picture of subgroups of the modular group. At the very bottom, I have this, and the corresponding subgroup is PSL2Z itself. And I construct some coverings. First of all, there's only one degree 2 cover, which is the one that I just draw on the blackboard. So this is a degree 2 cover. And I also have a degree 3 cover, which looks like this. So this is a degree 2, this is a degree 3. And, well, you can construct other coverings. For example, you can do the following thing. You can do the following thing. Well, For example, this is a degree 4 cover, which means that the subgroup, I gave you a procedure to find, so of course each time I must specify a base edge if I'm talking about subgroups. Here it doesn't matter which base edge I specify because this is Galois. However, here it matters. So this subgroup is going to have 4 conjugacy classes. 4 different conjugacy classes. Well, I see that some of you are growing impatient, so perhaps this is a good place to stop so that I can describe you tomorrow this panorama of a general picture of all subgroups of the modular group. Well, this will cost me my research talk, but anyway, I think that this is a rather better way of ending this story with something more understandable for everybody than my research talk. So, okay, thank you very much for your patience.